Welcome back to our mathematical course, Foundations of General Emergence Mechanics. If you've been following along, you know we've been carefully building our framework step by step. Today, in this explainer, we're diving into Episode 4, Coherence Stiffness, to uncover the missing dynamical correction. We really need to answer a fundamental question. What stops the vacuum's phase from being just a tilted variable and gives it genuine resistance?
Here's our path for today. We'll identify the missing phase ingredient, introduce the stiffness term, and decode the physical meaning of lambda. Then, we'll look at the schematic origin of the stiffness, explore the dynamical correction, and wrap up with a summary and reflection. Let's get started.
Section 1. The missing phase ingredient. Let's look at exactly what we already have in our mathematical toolkit. You might remember from Episode 2, we established the Z3 symmetric baseline, which gave our vacuum a foundational threefold structure. Then, in Episode 3, we introduced the Z2 chiral bias. That gave the structure a specific directional preference. So schematically, our phase potential right now is just the sum of that symmetric baseline and the chiral bias. Our current state is a landscape that is no longer perfectly symmetric. It leans. It has a tilt. But, well, here's the critical conceptual gap. Neither the baseline nor the bias describes an energetic resistance to phase displacement. It's a tilted landscape, sure, but it is entirely non-resistant. Okay, let's dive into this a bit more. The baseline plus the bias gives our vacuum structure and direction, but what we desperately need right now is finite resistance to phase displacement. Without it, the landscape is just mathematically slanted. It isn't dynamically stabilized. We need a term that actually measures the energetic cost of pulling the phase away from its center. We need holding power. Which brings us to Section 2, the stiffness term. This is how we're solving the problem.
Here is the crucial new mathematical component. Instead of a simple tilt, this term assigns a specific, measurable energy cost to pulling the phase away from its preferred coherent center. It transforms our landscape into something that actively fights back when disturbed.
Let's carefully break down the architecture of this equation. The angle theta 0 represents our preferred coherent phase center, basically the sweet spot. Now notice the quadratic form of the equation. This is incredibly important. Because it's squared, it means the energetic cost grows steeply as the displacement grows. A tiny nudge costs a little energy, but a large displacement? That is heavily penalized. And the severity of that penalty, the strength of that resistance, is governed by a brand new controlling parameter, lambda. Moving on to Section 3. The physical meaning of lambda. So what exactly is lambda? Now, what's really interesting here is that lambda is not a new fundamental force. You shouldn't think of it like electromagnetism or gravity. Instead, think of it as the effective rigidity of the phase-locked vacuum. It's like a cosmic shell elasticity. It is literally the energetic cost of distorting the locked structure, and it actively prevents local decoherence. To make this perfectly clear, let's use a physical spring analogy. Just like Hooke's law dictates that a stiffer spring fights harder against being stretched, lambda represents the stiffness of our phase. Pulling the phase away from its coherent center creates an energetic snapback. If lambda were extremely large, our phase would be essentially frozen in place, perfectly rigid and unyielding. Conversely, if lambda were extremely small, well, the spring would be incredibly loose. The phase would wander freely, and stable structure would dissolve, kind of like a guitar string that's too loose to hold a note. Lambda is what makes coherent structure dynamically resistant, rather than merely geometrically preferred.
Section 4, Schematic Origin of Stiffness. Let's look under the hood.
Looking under the hood, we find a very important caveat. This is a schematic representation, not a final first principles derivation. At our current level of theory, stiffness is treated conceptually as arising from integrating out fast fluctuations around the locked vacuum. So while this isn't the final closed form, it gives us the precise conceptual direction we need to proceed. Looking at the components, we can see how this stiffness mathematically emerges from three distinct physical scales. The vacuum amplitude squared sets our baseline scale. The orbifold cutoff squared provides the boundary scale of the integration. And finally, the geometric factor accounts for mode coupling and the underlying embedding geometry. The vital takeaway here isn't to memorize a final formula, but to recognize that vacuum amplitude, cutoff scales, and geometry combine dynamically to generate this crucial effective vacuum rigidity. Section 5. The dynamical correction. This is the conceptual payoff. So the crucial point really comes down to these three steps. First, symmetry gives the vacuum basic structure. Second, bias gives that structure directional preference. Third, and this is today's breakthrough, stiffness gives the structure genuine elastic resistance. Why does this matter? Well, without this third step, any attempt to analyze where the system eventually settles would be completely ungrounded. We cannot have a meaningful elastic correction without elasticity itself.
Section 6, Summary and Reflection. Let's solidify the concept.
Bringing this foundational narrative together, the Z3 baseline sets the foundation, resulting in a symmetric structure. The Z2 bias adds an asymmetric tilt, resulting in a directional preference. And coherent stiffness introduces a quadratic energetic cost, giving us genuine elastic resistance. This completely dynamically resistant framework is the absolute prerequisite. We cannot honestly discuss the final closure story, or where the phase ultimately locks, without having this energetic holding power firmly in place.
I want to leave you with this final thought to ponder deeply. If the bias term tells the phase which way the landscape leans, what exactly does stiffness add? Does it merely add resistance to motion, or does it dynamically enforce the selection of a preferred coherent center? Think on that distinction, because in Episode 5, we'll use this very framework, complete with its new stiffness, to derive the 15-degree shift and begin our road to the final 255-degree attractor. Thank you for your focus today. I look forward to exploring that derivation with you in the next explainer.